Hello everyone, I am Dr. S.V. Anandi, Associate Professor from the Department of Artificial Intelligence and Data Science at the Ramco Institute of Technology. Today I will be presenting a detailed session on search algorithms which form the foundation for problem solving in artificial intelligence. It is used to understand the behavior and analyze their strengths and limitations. Let's begin. This slide shows the classifications of search algorithms in AI. Search algorithms are divided into two main types, uninformed search and informed search. Uninformed search does not use any extra information about the goal. It explores the search space blindly. Examples include breadth first search. It explores level by level. Uniform cast search. It picks the lowest cast path. Depth first search. It goes deep into one branch. Depth limited search. It is a DFS with a depth limit. Iterative deepening DFS. Repeated DFS with increasing depth. Bidirectional search. It searches from start and goal simultaneously. On the other hand, informed search uses heuristics, meaning additional knowledge to guide the search. Main examples are best first search. It chooses the most promising node. A star search. It combines pathcast and heuristic to find optimal solution. So in simple terms, uninformed search means no extra knowledge. It is a blind exploration. Informed search means guided search using heuristics. Next, in AI, search algorithms are generally divided into two main types, uninformed search and informed search. Uninformed search is also known as blind search. It does not use any domain knowledge behind the problem definition. Informed search, on the other hand, uses heuristics or additional information to guide the search process more efficiently. In this session, our focus will primarily be on uninformed search strategies and we will be compare them at the end. Next, search data structures. To understand search algorithms, it is important to know the underlying data structures. Queue and stack are used in these data structures. Queue is mainly used for BFS because they follow the FIFO principle, first in, first out. Stacks are used in DFS because they follow LIFO, last in, first out. The basic operations we use include is empty, pop, top and add. These operations determine how nodes are expanded during the search. Breadth first search. Breadth first search is commonly called BFS. It explores nodes level by level, starting from the root. This algorithm is especially useful when all actions have the same cast. BFS is implemented using a queue, ensuring that the smallest unexpanded node is always selected next. In BFS, we use two basic operations, NQ and DQ. So NQ is the operation it is used to insert the data. DQ is the operation is it used to remove the data. This slide explains two basic terms used in graph traversal like visiting and exploring. On the left side we use visiting a node. Visiting simply means selecting or reaching a particular node. For example, starting at a node A, we are only marking the node, not moving to its neighbors yet. On the right side, we see exploring a node. Exploring means we not only visiting the node, but also check all its adjacent or connected nodes. For example, after visiting A, exploring it means we look at its neighbors like B and D. So in short, visiting means selecting a node. Exploring means checking all the neighboring nodes connected to it. Steps involved in breadth first search. Here are the key steps in breadth first search are. In the first step, we start with an empty queue. Next step is you have to insert a starting node. Next, while the queue is not empty, remove the friend node, explore it and add all its children. This search continues until the goal is reached or there are no more nodes to explore it. In this step, here we have to take the empty queue. After that, you have to select a root node A. So it is a node visited as starting node, and then it is expanded its children like B and C. It is also included in the queue. After that, B and C are explored here. Here we know the node D, E, F, G are the children of B and C. D, E, F, G are called leaf node. Here there are no more explored nodes of its children. So it is a last level of BFS. BFS advantages. So BFS will provide a solution if any solution exists. BFS guarantees binding a solution if one exists. If multiple solutions exist means BFS returns the one with the fewest steps. Disadvantages. It requires large memory to store nodes at each level. If the solution is deep, BFS takes significant time and space. Next, uniform cast search. Uniform cast search or UCS is commonly used when each edge in the graph has a different cast. UCS does not look for the shallowest node. Instead, it always expands the least cast path. It uses priority queue where the node with the minimum cumulative cast is expanded first. UCS is implemented using a priority queue instead of simple queue. Path cast by search to provide a solution. Its advantages. UCS is guaranteed to be optimal because it always selects the least cast path. Disadvantages. It may ignore the number of steps and focus only on the path cast. It may get stuck in exploring long low cast paths. DFS, depth first search. So DFS expands the deepest unexpanded node first. It goes as far down a branch as possible before backtracking. DFS uses a stacked data structure which allows the most recently discovered node to be explored next. So compared to BFS, DFS uses less memory. DFS problem. So here in this, A is taken as a start state and G is taken as a goal state. This slide shows a typical DFS scenario. You can see how the DFS algorithm quickly moves deep into the graph but may miss solver solutions because it prioritizes depth over breadth. So in this example, A is taken as a starting node and it is inserted into the stack, and it is taken as a visitor node. After that, A is expanded here. Here B is a next neighboring node and it is also stored in a stack and it is also taken as a visitor node. After that, B is expanded its neighbors. It is E. E is also taken as a visitor node and also it is stored into the stack. And again, F is stored in the next neighboring node of E. It is also taken as a visitor node and it is stored in E. F is not a solution, so you have to backtrack to E and then expand the next neighboring node E to G. G is our solution node. So this is a DFS order for our problem. So in this example, here also A is taken as a starting node and M is taken as a goal node. So here A is expanded here. So A is expanded, its children are B and C. Again B is expanded to D and E. D is again expanded to H and I. So H and I are not a solution node. So we have to backtrack to D and again backtrack to B. Then it is expanded to E. And J and K are its children. It is also not a goal node. So again you have to backtrack to B to A. So again it is expanded to C. C is again expanded to F and G. So F is again expanded to L and M. So M is our goal node. So this is a DFS order for our problem. So advantages of DFS. DFS uses very little memory. It may reach a goal faster than BFS if the solution lies deep in the correct path. Disadvantages. DFS may re-explore states many times. There is no guarantee of completeness or optimality. DFS may also fall into infinite loops. Depth limited search. So depth limited search is a variant of DFS where a depth limit is imposed. Nodes deeper than the limit are treated as if they have no children. This prevents the search from going indefinitely into deep or infinite branches. So in this example, we have taken as a limit as 2. So 1 is a start node and 11 is a goal node. So here our solution is not reaches to our level 2, not to take a goal to found. So it is an incomplete solution for the deepest search method. So these are the failure conditions of depth limited search. There are two failure conditions in depth limited search. One is standard failure and another one is cutoff failure. Standard failure means there is no solution in the tree. Cutoff failure means the limit was too small, so the search ended prematurely. Cutoff indicates that increasing the limit may help reach a solution. Advantages and disadvantages. Depth limited search is memory efficient and reduces the risk of infinite loops. However, if the depth limit is set incorrectly, the search may miss the solution entirely. DLS is not always complete. Disadvantages. Depth limited searches is also disadvantages of incompleteness. Iterative deepening DFS. Iterative deepening depth first search or IDDFS combines the best features of BFS and DFS. IDDFS repeatedly runs depth limited search with increasing limits 0, 1, 2 and so on. This allows us to find the slowest solutions like BFS while using memory close to DFS. IDDFS nodes at the deepest level are expanded once, while nodes near the top may be expanded multiple times. Although repeated work occurs, the bulk of search happens at the deepest level, making the method efficient in practice. So this is a traversal of BFS and DFS. This slide visually compares how DFS and BFS traverse the graph. BFS expands level by level and DFS depth by depth. This comparison is essential to understand why IDDFS combines these strategies. So IDDS problem example. This slide shows a problem example why IDDFS gradually increase the depth limit evenly reaching the goal node. Each iteration explore deeper levels but maintains the memory and advantage of DFS. IDDFS advantages and disadvantages. Advantages: it combines the minimal memory usage of DFS and completeness of BFS. It is efficient for large search space with unknown depth. Disadvantage: repeated expansion of upper level nodes. It increases computation time. Bidirectional search algorithms. Bidirectional search algorithm starts from two directions. One search begins at the start node and another begins at the goal node. This search stops when the two search frontiers meet. This diagrammatically reduces the search space because instead of exploring b power d nodes, it explores roughly 2 into b power d by 2 nodes. So bidirectional search, in this example, the forward search begins at node 1 and the backward search begins at node 16. Both searches meeting at node 9. This point of intersections gives us the solution path with far fewer node expansions. Bidirectional search pros and cons. Here the advantages are much faster than unidirectional search and it requires less memory. The disadvantages are it is hard to implement, it requires knowing the goal state clearly, backward actions may not always be defined. So this is a comparison of uninformed search algorithms. The final comparison slide summarizes all uninformed search strategies: BFS, DFS, UCS, DLS, IDDFS and bidirectional search. We compare them based on the completeness, optimality, time complexity, space complexity. Understanding these helps choose the right algorithms for different AI algorithms. Thank you. Thank you for listening to this presentation on search algorithms in AI. I hope this session gave you a clear understanding of how different search strategies work and when to use them. Thank you.